We're not restricted to using interpolation only for one-dimensional systems, but for two-dimensional, three-dimensional, and higher. In this course, though, we're only going to focus on 1D and 2D systems. So in our 2D system, we have two independent variables, and we have one dependent variable, or we could have multiple dependent variables. We're going to focus on two independent, one dependent variable. So what it's going to do the interpolation, it looks at what I'll call kind of the x direction, what two x values is our interpolating point between, and what two y values is our interpolating point between from the measured data. And then it's going to make a similar calculation to how 1D interpolation was being done. And we're going to use the interp2 function here rather than the interp1 function. And unlike what we saw in one dimension, where the spacing between the measured data didn't matter as long as it was strictly increasing, strictly decreasing, for the built-in interp2 function, all of the data points must be evenly spaced for this to work. Now there's other methods besides interp2 that you could use non-evenly spaced data, but we're not going to focus on that in this course. Now you can see an example to use our 2D interpolation here. We have this data from 9 thermocouples measuring temperature on a plate at specified intervals across the horizontal dimension and vertical dimension of the plate. So our x locations are at 0. I'll just type these in manually, 0.5 and 1. And our y are at 0, 1, and 2 meters on this plate. And the temperature, those are our independent variables. And our temperature at 0, 0 is 80, 100, 120, 120, 130, 135, 130, 142, and 149. What we want to do is using interpolation, since we only measured at 9 points, we're going to use interpolation to kind of fill in everything in between to make a contour plot of what does the whole temperature field look like across this plate. So what we are going to do is, I'll call this little xi, is going to be a lin space between 0 and 1. I'll fill with, I'll just keep it small for now, 100 points. So that's going to fill in x locations between 0 and 1. And for y, going between 0 and 2, and I'll use 200 points for this. And because we're working with this two-dimensional data, it's going to be nice to use meshgrid out of this. So I'm going to turn these into vectors like we saw before using meshgrid on xi and yi. Right, so remember, xi and yi are just going to be vector values, but then big xi and big yi are converted into these matrix values. So the corresponding elements in x correspond to those in y. So the first row, first column of x corresponds to the first column, first row of yi. Now what I can do is do my interpolation. So using interp2, I'm going to take my measured points, x and y, I can leave those as vectors here, my measured temperatures, and then I want the matrix of x values I want to interpolate at, and the matrix of y values I want to interpolate at. And what I'm going to get out, since the temperature was originally a matrix, this is going to give me another matrix when I run this. So we see I have a large matrix of values here when I run interp2. So this is filled in the spaces in between these only 9 temperatures I actually took. I can visualize this. I'll use a filled contour plot. So I have xi and yi, and now the estimates, I guess I have to save this, I'll call it TE here. So the estimates of the temperature using the interpolation. Put a color bar in, and I want this to be jet since we're talking about temperatures. And I can specify how many contours to use, so I'll update that a little bit. So this is a visualization of what the temperatures are. So at 0, 0, from our data we had it was 80, and then it has kind of this gradation to these different temperature measurements that we were making up until 1, 2, where we measured that was 149. Now by default, interp2 also uses linear interpolation. So that's going to look exactly the same. Right, so I added my labels. I'm setting my axes to equal here. And now if I rerun this, I get my new temperature distribution. So you see it rescaled the axes. So now the same distance in the horizontal axis is equivalent to that distance in the vertical axis. So you see here 1 meter is this long in X, 1 meter is also that long in Y. So now it looks like what the plate would look like to scale, and now the temperature field that's on top of it is also proper to